So we were looking at the heap sort algorithm last time. So, so the problem is given an array of integers like this. We want to sort it in the increasing order of the values. So the first step is to build a max heap of this array. So as you know, we can do all the manipulations with an array itself. So first build the max heap for the given array, and then the second step is once you get the max heap, you start moving the integers to their final positions. So you go through a sequence of iterations. In each iteration, you move the root node to its last position in the accessible portion of the array. So to begin with, the entire array is accessible, so you move the root data to the last index in the array, and once you move it there, this 10 goes there, that index becomes not accessible anymore. So the accessible index is from 0 to 8. And now what you do is you kind of swap actually the root node with the element in the last index, accessible index. So 3 becomes like a kind of a temporary root. So you have to again reheapify the root index. So how you reheapify is compare the data at that index with the data of the two child node index. So in this case 3 is less than both 8 and 9, and we want to have max heap. So swap 3 with the larger of the two child node data. So when 3 comes down here, the max heap property may be affected further down. So what we have to do is we have to again compare the data of the two child nodes. In this case again 3 is less than both its child node data, so swap with the larger of the two child nodes, and if we have a tie, go in favor of the left child, and then swap 3 with 5 here. So when 3 comes here, this is the leaf node position, so we don't need to go further down. So we need to repeat that as a sequence of iterations, and every time we move the root node data to the last accessible portion, that data stays there and that index becomes not accessible anymore. So we did this example last time. We'll go through one more example in detail, and we'll proceed further. Now look at the code for that before we go to the example. So we saw the code last time for how to reheapify. So let us build on top of that code to run the heap sort. So here I'm assuming that you already have the array, so and then you have kind of built a max heap of the array. Okay, so you go through a sequence of iterations. So the iteration index is 0, iteration index is array size. Then as we just saw, the first step is to move the root node data, which is at index 0, to the last accessible portion. So in any iteration corresponding to iteration index, the last accessible index is going to be array size minus 1 minus iteration index. So why is it? Think about it. So if iteration index is 0, array size minus 1 minus 0, which is array size minus 1. That's the last accessible index. So it makes sense. If for a given array size minus 1 is the last accessible index. So that's why I indicate for iteration index starting from 0. The last accessible index of the array is going to be array size minus 1 minus iteration index. So you do the swap. So this is a code for swapping the element at index 0 with the element at array size minus 1 minus iteration index. Now once you do the swapping, so the element at the root node index goes to this index, and the element at this index goes to index 0. So because of that, the max heap property may be affected. So what we have to do is we have to reheapify. So you have to call the rearrange heap array function. We saw the code for this last time. So we pass the array pointer, then the size. Okay, so if you go back to the rearrange heap array function, the 3 arguments it takes are of follow what logic. So let me go through that. Okay, so This is the way we set up the function for rearrange heap array, the array pointer, the array size, and the index starting from which you want to reheapify. Now, when I say array size, it's basically the number of elements in the accessible portion. Now, for a normal array, the entire array is accessible, so array size is the number of elements in the accessible portion. So now we want to pass the parameters carefully here, because the number of elements in the accessible portion keeps changing with the iterations. So how do we do that? So the number of elements in the accessible portion could be indicated as array size minus 1 minus iteration index. So why is that? So in the first iteration with iteration index 0, after we do this, we make this last index not accessible. So the number of elements is going to be array size minus 1 minus 0, which is array size minus 1. So to begin with, we had the entire array, which is array size, being accessible. But now after this swapping, the last index is not accessible anymore. So the number of elements are accessible. So this is not the index. This is the number of elements that are accessible is going to be array size minus 1 minus 0, which is array size minus 1. So you pass array size minus 1 minus iteration index, and this is the index starting from which you want to reheapify, and that stays always 0 because you always swap to the root with the root index. So this is the index starting from which you want to reheapify, and this is a recursive function, so it will take care of reheapifying if you move the data further down and so on. Okay, so just one single call this to this function will take care of the reheapify process. And here I just run a for loop to print the contents of the array after each iteration, so we can see how the integers are moving around. Okay, so this is just for kind of tracking what's going on with the iterations. So as I mentioned here, the active portion or accessible portion is from index 0 to array size minus 1 minus iteration index, and this is the size of the array after the size of the active portion after the swapping. Okay. Now, so let us go through one more example. So you are given the original array. Now let us go through the entire process. So for the first step, as I said, is to build a max heap of the array. So how do we build that max heap? So we just now first build an essentially complete binary tree. So how you build an essentially complete binary tree? Just go top down, left to right. So the root node is level 0. We have the data at index 0, 13 from the given array. Then its two child nodes at level 1 are going to be 22 and 18. So those are index 1 and 2. Then for index 1, so we know also from the heap property that for index j, its two child node index values are 2j plus 1 and 2j plus 2. So 2 times 1 plus 1 is 3 and 2 times 1 plus 2 is 4. So the next two data values 27 and 14 go to index 3 and 4, and then the next value will go to index 5. So this is an essentially complete binary tree. So now we have to change this to a max heap. And how we do the max heap is start reheapifying from the last internal node all the way to the root node. So the last internal node is going to be index 2 in this case. And also there is for any array of size n, the last internal node will be at n over 2 minus 1. So in this case, there are 6 elements, so 6 over 2 is 3, 3 minus 1 is 2. So that's the last index for the last internal node. So again, now we have 18 and 23 here. So we want to build a max heap. So what we have to do is swap 18 and 23. So 23 comes here, 18 comes down. Now this is a leaf node position, so we don't have to check further down. So after the swap, we have 23 and 18 here. So then reheapify the node at index 1. So you have 22 and 27, 14. 22 is less than 27 but greater than 14. So we have to compare with both the child nodes. So in this case, so we have to swap 22 with 27, so 22 comes here, 27 goes here. So again, this is a leaf node position, we don't need to check further down. Now reheap if at index 0, so 13 compared to 27 and 23, it's less than both the child nodes, so you have to swap with the larger of the two child node data. So swap 27 and 13, so 27 comes here, 13 comes here. Now this is not a leaf node, this is an internal node, so we have to compare further down. So 13 compared with its two child nodes 22 and 14, less than both. So swap with the larger of the two child node data, so 13 comes here, 22 goes here. So again, that's a leaf node position, so we don't have to compare further down. So after this process, we have built a max heap of the original array. So as I showed in the other examples before, we can do all these things in the array itself. The heap is just for visualization, the binary tree format. Alright, so in an exam, we have to show both the binary tree based visualization as well as the changes in the contents of the array for each iteration. Alright, so we have now the max heap. So now what we have to do is again, second step is to go through a sequence of iterations. We just saw the code for that. So in each iteration, move the root node data to the last accessible portion of the array. So to begin with, the entire array is accessible. So move the root node data, which is 27, to the last accessible index, which is 5 in this case. So in an array of size 6, that index is going to be array size -1 minus iteration index for iteration index 0. So once we move that index becomes not accessible anymore. So the accessible portion of the array is from 0 to 4, and the number of elements is array size -1 minus iteration index. So once you move once you do the swapping, so 18 goes to the root node position, 27 comes here. We have to make sure the heap property is restored. So compare basically do reheapify at index 0. So 18 compared with two child nodes, 18 is less than both, so we have to swap with the larger of the two child node data. So 18 comes here, 23 goes to the root node position. Now you see here, this index 2 is a leaf node logically, because this index is not accessible anymore. So we should not swap further down. So we have to be careful when we do this reheapify in the second step of the heap sort. So once certain portions of the array becomes not accessible, you have to keep track of them so that you decide whether to swap, move further, check further down or not. So in this case, at index 2, this is a leaf node position, so we should not do any further swap down. So 18 stays at index 2. So this is now the updated heap. So now for the next iteration, you move the root node data to the last accessible index of the array, which is index 4. So 23 comes here at index 4, 14 becomes a temporary root data. So now again reheapify the root node. So 14 compared as 22 and 18, it is less than both. So swap 14 with the larger of the two child node data. So 14 comes here, 22 goes here. So now this is not a leaf node because it has one child node index that is accessible. So we have to compare 14 with this child node index 13. Of course, this index 4 is not accessible, but index 3 is part of the accessible portion of the array. So we have to compare 14 with 13, and 14 is greater than 13, so we just leave it as it is. In this case, if it was, say, instead of 14, 12, 12 with 13, 12 is less than 13, so we have to do a swap. So since here 14 is greater than 13, we just leave it as it is. So now this is the updated heap. So now in second iteration, swap 22 with the last accessible index data, so 13. So 13 becomes a temporary root, 22 comes here. So of course you have to show the corresponding changes in the array after the swap and after the reheapify. So 13 compared with two child node index, so 14 and 18 are the data. So 13 is less than both, swap with the larger. So 13 swap with 18, 18 becomes the root, 13 comes here. So that's what you should show here too. 18 becomes the root, 13 goes to index 2. Now index 2 is a leaf node position, so you don't have to or should not compare further down. So after this iteration you have the heap like this. So now again move the root node data with the last accessible index, which is index 2. So 18 comes to index 2, 13 goes to the root node data, and you have to make sure it is reheapified. So 13 compared with 14, 13 less than 14, so do the swap. Now when 13 comes here, this is the leaf node position. So in this case, both the child node index are not accessible anymore. So should not compare 13 further down and do any swapping. So after this iteration, 14 becomes the root and 13 goes here. Now in this iteration, 14 can be swapped with 13 because this is the last accessible index. So 14 comes here and 13 becomes the root node data. Now that's the only index that's also accessible, so we are done with the iterations now. So you notice here for an array of size 6, we go from iteration 0, 1, 2, 3, 4. So we have n minus 1, 5 iterations. And in each iteration what we do, so if you look at the time complexity of this heap sort algorithm, what we do in each iteration is swap the root node data with the last accessible portion and then reheapify. Now at the worst case, the reheapify process will go all the way from the root node index to the last level. So the time complexity of reheapifying for each iteration would be log n, because the log n is the number of levels in a binary tree of n nodes. So we have n minus 1 iterations, and you have log n as a time complexity for each iteration, and as a worst case time complexity, because we may not need to go all the way further down. So it's a big O of log n, that's the time complexity for each iteration. And you have n minus 1 iterations, so that's going to be n log n, big O of n log n for the second step. Now if you go through, if you remember what we did in the first step of the max heap, that's also a big O of n log n process. So we basically have two n log n stages. So the first step stage is to build the max heap of the given array. That is an n log n time complexity process. And the second step is to kind of move the root node and the max heap to its last accessible portion and go through a sequence of iterations like that. So that step is also an n log n complexity step. So with n log n plus n log n is still n log n. So that's why the time complexity of heap sort is n log n overall, big O of n log n. Now if you look at the space complexity of heap sort, we do all this moving around of the data with the given array itself. So we start with this original array, that's the input array, and then do all the moving around of element and values and build a max heap of it. And then we can again do all those moving around of the root node data with the array itself. So we don't really need any additional memory that grows with the input size. We may use some temporary variables to do the swapping, but the number of temporary variables we use does not grow with the input size. So that is why heap sort is an in-place algorithm. That means its space complexity is theta of 1. So it does not use any additional memory that grows with input size. So this is something you need to know. So heap sort is a very good algorithm actually, because it does not use any additional space that goes with input size, theta of 1 space complexity, as well as it's an n log n time complexity. So the I think I should have said this before. When you do comparison based sorting, so what we did is comparison of the two values and do the sorting, right? So several sorting algorithms do this approach of comparison of values and then sorting. So any comparison based sorting algorithm, you cannot do better than n log n, and heap sort really accomplishes that. So it's an n log n time complexity sorting algorithm, and is also in place. The other algorithm we saw in this course, which was selection sort, it's also an in-place sorting algorithm. It does not use additional memory that goes with the input size, but it is an n square sorting algorithm, whereas heap sort is n log n sorting algorithm. So when you compare the performance of the two, you will see heap sort will do better. So this is something you need to know between the two sorting algorithms. So I'll stop here to save the video. So if you have any questions, you can type in the meantime.